Okay, so what kind of answers did we come up with there? Somebody asked, what country are you in? Well, I mean, that could be part of your answer too. It might have an impact. So what did you think of?
It's not zero, it's just food, if you're in like a restaurant.
So what threshold would you use? Say a thermometer, you're going to sell this as a thermometer to restaurants. So like in the fridge, I think stuff has to be stored at 4 degrees or lower or something. So you put this in the food or you put this in the fridge. If it's higher than 4 degrees, it'll show red, which means it's too hot. If it's whatever, 4 degrees or lower, it's blue, that's good. I mean, body temperature is a good one as well. That's like healthy body temperature is 36 or something, isn't it? So you could sell that to hospitals. Now, actually, you might want to make the threshold, it's 36 point something, isn't it as good? Like 37 even probably isn't battle stations either, do you know? You might decide maybe at 37 and a half or something, or even 38, at that point, someone has a temperature that you have to do something about. Maybe 37 even isn't the end of the world. I don't know. You could talk to some doctors and some nurses and figure out exactly at what point is that meaningful. I mean, ever so slightly above normal temperature probably wouldn't be as useful as a little bit above. So you could sell that to hospitals. Because let's face it, I mean, actually, really in a hospital, they really want to know, have you a temperature or not? Perhaps they want to track it, see it's going in the right direction maybe. That's of use. You couldn't tell that from one bit. But as we saw with other things, the meaning of the bit is up to us to decide. That one bit can do a lot. Anybody other suggestions? That was it. Thermostat. So what threshold, what would you set for zero? Like when would it show 0, when would it show 1? When would it show blue, when would it show red? What would be the threshold?
It's like you set a temperature above or below.
So the comfortable temperature for a room, whatever that might be. And of course, depending on who you are and where you are, that might vary. Some people are a bit colder than others. Any other suggestions?
Fish tank, tropical fish.
Oh yeah, you could have a fish tank, a tropical fish, whatever temperature that's supposed to be. You could sell those. You could probably sell 5,000 of those to people who have fish tanks. Make some money. People who have tomatoes might want to know if it's freezing or not outside. So, below 0 might be blue and above 0 would be red. So, you need to figure out where the threshold is between hot and cold. And depending on how you set it up, that may be more or less useful. So where do you put it? That's the question. So in the hospital, we figure you want to tell if someone has a temperature or not. Like in a hospital, it doesn't really matter if someone's temperature is, 1 degree or 2 degrees, like they're dead. Do you know? All you're interested in is have they got a high temperature or not. There may be, for example, a temperature below which someone is at risk of hypothermia. So maybe you might sell 5,000 of those to the RAF or something to put in helicopters. Are you a candidate for, anti-hypothermia treatment or something? This guy here, he's not training for the Winter Olympics by the looks of him. So he's probably interested in, is it like too hot to go training outside? So maybe if you're an athlete, anything above, 30 degrees or something, you're not allowed to train outside or something. It's not something we'd have much experience of in Ireland. It's never too hot to go outside. A thermometer in Ireland, you're going to sell it to Irish people to see, is it too hot to go out? Or maybe is it too cold to go out? Let's say is it too cold to go out thermometer? when is it too cold in Ireland to go out? Do you know? I mean, below maybe 5 degrees, we'd probably find it cold. Now, if we were selling this thermometer to people in, Alaska, if we were going to, ship them to Alaska and try and sell them there, I mean, telling someone whether it's below 5 degrees or not is probably, a waste of their time. If you're selling it to Alaska, maybe the threshold there is something like, I don't know, it's minus 20 before it's a cold day or something. I don't know. Similarly, if you're going to ship them to Spain and try and sell them there, maybe people in Seville want to know if it's too hot to go out. So maybe I'd say, it has to hit 30 in Seville before it's considered, a very hot day. Whereas, in Ireland at about 22, the roads start melting. So, depending on what you're going to do, you're going to set it to something different. But that threshold there is what's important. Now, if we had a 2-bit thermometer, right? It might go from like blue, yellow, orange, red. So it might be, cold, a bit warmer, warm, and hot. So with 2 bits, we might have 4 levels, 4 thresholds. Well, there's only 3 thresholds if you think about it. But we have 4 levels. And we call those 4 levels quantization levels. They've got a name. And again, where do we put those, I mean, so if it's hot, it's, could show red. If it's warm, orange, warming up, or okay, yellow. And if it was blue, it's cold. But again, where we set those is arbitrary. And depending on what we're going to use it for and where we're going to use it, it could be in different places. So in the hospital, we might decide that a temperature of 33 or lower is like freezing cold, which is very cold for a human being. 33 to 36 maybe even 33 to 37 might be like okay. Maybe 37 to 39 could be the next level up. And then anything higher than 39 is like, oh my God, throw every antibiotic you've got at that person. And that might be enough in a hospital. This athlete who's running in the heat might have different levels of, okay, should I wear my tracksuit? It's fine, it's getting a bit hot, and no, I can't go out today. If you were to look at the quantization levels for a thermometer, that would be useful to Irish people. Like to kind of be, Janie Macros is below 5 degrees and frozen. 5 to 15 might be grand. 15 to 20 or even 22 might be a hot day, and anything above 22, the red one, like take the day off work, take off all your clothes and go to the beach. It doesn't take much for Irish people to bam out, as you know. Okay? In Seville, anything below 15 might be Jesus, we're frozen. 15 to 20 might do whatever. So depending again on the context, on the application, you might have different thresholds. So you have different quantization levels. That's what they're called. Okay? Now, so digitization happens in 2 stages. The first thing is called discretization. Okay? And that's where you take a reading of the analog signal or the analog value. So the actual temperature might be 17.354735374, whatever. Okay? This value is called a sample. You may hear DJs and audio people talking about sample rates. Actually, there's a bad example now because, of course, sampling, DJs sample as well. It's a different sample. Sorry, DJ sampling and audio engineer sampling, different. Okay. Now, at this point, the sample is considered to have, infinite precision. And the next part of the process then is quantization. Now, in reality, the discretization and the quantization typically happen at the same time instantaneously, but conceptually they are separate. And quantization then is the process of deciding which of the quantization levels does this analog value, does this sample fall into. So in this example here, 17.354 blah 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 is the 1, 2, 3rd highest quantization level, and that gives us the orange LED on our 2-bit thermometer. So you're looking at the real world value and seeing what it is, and then you're seeing which of these slots does it fit into. The example I usually use in class involves bricks, but this cardboard building doesn't have any bricks. But if I wanted to have a rough measure of everyone's height, I could stand them up against the wall and just count how many bricks tall they are. So that wouldn't be a very precise measure. Someone who's 180 centimeters and someone who's 184 centimeters might all be in that whatever 9th brick or something. So you look at the real world analog value and then you see which of these slots it fits into. Get the idea? So that's what your 2-bit 4 LED thermometer would be doing. Taking the real value, and then all you know then is the 3rd one. So all we know is that the temperature is somewhere between this, and that's all we know. Now, the more quantization levels you have, the more accurate the digital representation is going to be. So depending on the application, you may need quite a lot of precision or not. So Walter White, when he's cooking his meth, probably was very fussy about the temperature at different parts of the process. And he needed quite a lot of precision. So he wouldn't have splashed out on one of our 4-bit or one of our 2-bit thermometers. He'd probably gone for something a bit more precise. Interestingly, in hospitals, they're really only interested in, are you sort of, 1 decimal place? Is your temperature 34.1, 34.2, 37.5? We don't need loads and loads of decimal places. There may be other applications where, you need more. Again, depending on the application, different quantization levels and different degrees of accuracy, different levels of precision would be required. If the weatherman told us that today's temperature is going to be somewhere between, 0 and 20, we're yeah, he'd be right anyway. But that wouldn't be telling us much in Ireland. Now actually, Spanish weathermen saying that might be saying a lot. An Alaskan weatherman saying that might be saying a lot. But an Irish weatherman saying 0 to 20, yeah, He'd be right 360 days of the year without saying anything. Okay? Now, another thing then that we're very interested in is measuring something over time. And this is where another concept comes in. So we take our sample and we slot it into one of these quantization levels. If you have 2 bits to play with, you'd have 4 quantization levels. If you have 16 bits to play with, you have how many thousand quantization levels. So the accuracy of the representation would depend on how many quantization levels you have. Sometimes we need to measure those things over time also. So here we have an analog signal. It could be the temperature over the year, for example, or it could be a sound wave. It could be some analog value. And what we do is we sample it at regular intervals. Now, when we looked at the quantization levels, we could be fairly arbitrary about where they were. You know, some could be bigger than others, and that's okay. Generally, when you're digitizing something over time, or space as it happens, the intervals are fixed usually. They can't be arbitrary. And so each sample then is quantized. Well, here we're not quantizing it, we're doing the, what did I call it? Does anyone remember the word? Yeah, it was that important. It wasn't. Discretization, yeah. So here we're looking at each point in time, we're looking at the signal and we're seeing what it is. And then we figure out each one of those fits into which quantization level. So let's see that again. So we figure out every so often we're going to look at the sample. So if this was the temperature in Ireland, we might say every day at noon we're going to measure the temperature. Or if it's a sound wave, it could be you might do 22,000 of them in a second, as it happens. You do a lot for sound waves. We look at the values and then we figure out which quantization levels they fit into. Now, you may not notice here, the quantization levels I've used aren't actually equal sizes here. They might be at equal intervals or they might not, depending on the situation. And so all we know now then, for example, about this sample here is that it fit into this range. All we know about this sample here is that it fit in this range. All we know about this last sample is that it was somewhere in this range. Fits into that quantization level. So here then, what we have is our digital representation of that wave. And the first sample was in quantization level number 1. The next one was fit somewhere in 1. The next one was somewhere in 1. The next 4 were somewhere in 0, and so on like that. Now, there are two axes then for the accuracy and for the precision. Here I've got 5 quantization levels. 1, 2, 3, 4, 5. Obviously, if I had 50 quantization levels, the shape of this wave here would be a bit more precise. The shape of this representation would be crisper. Here I have samples, every whatever this is representing. If I increase that tenfold, then again, the precision would be much greater. So we can have precision in 2 different axes. You'd see those 2 axes manifesting themselves in, say, an audio file. So an audio file might be 44 kilohertz, which is 40,000 samples per second, and it might be 16 bits per sample. So you'd have 44 of these samples every second, and there could be 16 bits, which would be however many thousand possible samples. Or quantization levels, I said it wrong. Quantization levels. Or you might have 22 kilohertz, yeah, and 8 bits per sample. With an image, you might be talking about 800 dots per inch. So the sample isn't actually over time, it's over space. You're like, look here, take a sample, here, sample, here, sample, here, sample, here, sample, as a scanner might do. And then you might talk about the number of bits per pixel. And that's where we're going to see a lot of this. We're going to be talking about bits per pixel and stuff like that a lot. So the sample rate then is the frequency with which we look at the samples. And so for an audio file, like if you're ripping a CD, you know, that you paid for, of course, just for your personal use, of course. If you're ripping a CD, iTunes might give you the option, or the software you're using might ask you, you know, what sample rate do you want and how many bits per sample. No, actually, most of the time they just talk about how much data you want to use per second. They've kind of summed that up in that one value. But actually there's two things going on. There's a sample rate and the number of bits per second. But the more samples you have, the more accurate it is. So if this was the temperature in Ireland, and we took a sample every day, we could probably tell, you know, when winter was and when summer was and stuff like that. If we took a sample every hour, we would probably notice that, you know, we could pinpoint the days and the nights. And it might not tell the full story. If you took the temperature every day, for example, in California or Nevada desert, you might be able to see that it was quite hot a lot of the time. But what you wouldn't be getting by taking a sample every 24 hours is the huge variation between the hottest part of the day and the coldest part of the night. So it wouldn't be telling you the whole story, that you could roast to death during the day and freeze to death during the night. It might actually look like just, you know, very stable, because you're only seeing it once a day. Whereas if you took it once an hour, you'd capture that story. So the more samples you have, or the greater the sample rate, the more accurate the representation. If we half the sample rate here, you see that what we get, you know, doesn't quite, if you consider what we were trying to do way back, if this is the thing we're trying to represent, you can see that this thing here with very few samples doesn't quite capture it as well as this anyway. This isn't great, but it's vastly superior to this. So over time, you have a sample rate. That's the point here. And of course, depending on the application, the sample rate could be important. You know, in the hospital, if you're sick, they may come and check you every 2 or 3 hours. You know, checking someone every 40, 50 hours, you know, not a whole lot of use. Any questions on that?